Welcome. Today, we dive into the PD-1 and PD-L1, often called the brake pedal of the immune system. This mechanism allows cancer cells to escape detection. Understanding it has led to breakthrough therapies that are saving lives worldwide. Let's explore how it works, why it matters, and how we're turning this knowledge into powerful treatments. At the heart of this system are two molecules, PD-1 and PD-L1. PD-1 is a receptor present on T cells, our body's primary immune fighters. Its role is to prevent excessive immune responses that could harm healthy tissues. PD-L1 is its binding partner, and under normal conditions, it helps maintain immune balance. However, many cancers exploit this by producing large amounts of PD-L1. When PD-L1 on a tumor cell binds to PD-1 on a T cell, it sends a powerful inhibitory signal, effectively putting the T cell to sleep. This allows the tumor to grow unchecked. PD-1 is not always active. It appears on immune cells after they've been activated, serving as a built-in brake to prevent collateral damage. PD-L1, on the other hand, is usually kept at low levels in normal cells. But tumors change the rules. They dramatically increase PD-L1 production, turning their surface into a shield of "don't attack me" signals. This overexpression is a hallmark of immune evasion, allowing cancers to thrive despite the presence of immune cells. Structurally, PD-1 and PD-L1 are designed to fit together precisely. PD-1E's extracellular region recognizes PD-L1E's front beta sheet surface, much like an antibody recognizes its target. Once they bind, the cytoplasmic tails of PD-1 become phosphorylated, recruiting signaling proteins like SHP2. This sets off a cascade that dampens T cell activity at the molecular level, effectively neutralizing the immune response. Here's how the suppression unfolds. When a T cell encounters a tumor cell, its receptor binds to the tumor antigen. But if PD-L1 is present, the simultaneous PD-1-PD-L1 interaction overrides the activation signal. SHP2 is recruited and shuts down critical pathways like CD3 and ZAP70. The T cell stops proliferating, produces fewer cytokines like IL-2, and enters a state known as exhaustion. In this state, it can no longer effectively kill cancer cells. The influence of PD-1-PD-L1 extends beyond T cells. It strengthens regulatory T cells, which further suppress immune activity. It reprograms macrophages into a pro-tumor M2 state, encouraging blood vessel growth and tissue remodeling that supports cancer progression. Even natural killer cells, our rapid response immune attackers, are muted when PD-1 binds PD-L1. This creates an immunosuppressive microenvironment, where the tumor is protected on multiple fronts. Despite the success of PD-1-PD-L1 blockers, not all patients respond, and some eventually develop resistance. Tumors are adaptable. They may mutate proteins needed for antigen presentation, activate alternative immune brakes like CORT-LA4, or alter signaling pathways to downregulate PD-L1. Some tumors simply lack enough antigens to trigger a strong T cell response. Understanding these escape routes is crucial for designing next-generation therapies. The therapeutic answer to PD-1-PD-L1 evasion is checkpoint blockade. These are lab-made antibodies that physically block either PD-1 or PD-L1. By preventing their interaction, we release the brakes on T cells, allowing them to recognize and destroy tumors. Drugs like pembrolizumab and atezolizumab have been approved for a growing list of cancers, often with durable responses. PD-1 inhibitors are typically IgG4 antibodies to minimize inflammation, while PD-L1 inhibitors are IgG1 to enhance immune activation. To improve outcomes, researchers are combining PD-1 and PD-L1 inhibitors with other treatments. Chemotherapy can cause tumor cells to release antigens, making them more visible to the immune system. Radiation can turn tumors into vaccination sites, attracting T cells. Anti-angiogenic drugs improve blood flow and immune cell delivery. Dual checkpoint blockade, like combining PD-1 and CORT-LA4 inhibitors, attacks multiple brakes simultaneously. Targeted therapies against oncogenic pathways also downregulate PD-L1. creating a dual precision plus immune attack. In summary, the PD-1 PD-L1 pathway represents both a challenge and an opportunity in cancer therapy. By understanding how tumors exploit this checkpoint, we've developed drugs that restore immune function, while resistance remains a hurdle. Combination strategies and personalized approaches are paving the way forward. This is not the end, it's a new beginning in immune oncology. More targets sharing. See you next time.